All right, testing my mic here. You know what? That sounds way better. Let me just mute my. Yeah, let me just disable monitoring on my mic here. All right. Okay, there we go. Let us begin. Uh, why is my. I have to mute my other stream, the one that I have on YouTube. All right. Now that that's done, as always, I'm gonna continue learning my Pytorch course. We are gonna start from where we left off yesterday and let's see the progress that we make today. Yesterday we left off at the halfway mark. So yeah, let's I'm excited to learn see what we're about to learn today. So let's begin.
Hello, welcome to the video.
We have come a far way indeed. A long way indeed, rather I should say. Training desktop, discussing options. Yesterday, Danny here left us with a challenge to write out and see whether there were any improvement to our what our model after we implemented the relu layer. And apparently, seems like Collab has saved the results here. Maybe I'm looking at the wrong thing. Anyhow, the at the end of the day, no, it hasn't. The results haven't changed. So maybe there might be something I might be missing. So we're gonna check that out right now. Before that, let me run all cells. Here we go.
It's quite a big one. But if you've come
Do you want to become an expert in AI and machine learning? Well, Logic Mojo is here to help you get placed in.
welcome back. In the last video, we saw that the model that we've been building has some potential to learn. I mean, look at these predictions. You could get a little bit better, of course, get the red dots on top of the green dots, but we're just going to leave that. The trend is what we're after. Our model has some capacity to learn, except this is straight line data. And we've been hinting at it a fair bit, is that we're using linear functions. And if we look up linear data, what does it look like? Well, it has quite a straight line. If we go linear, we just search linear. What does this give us? Linear means straight. There we go, straight. And then what happens if we search for non-linear? I kind of hinted at this as well. Non-linear. Oh, we get some curves. We get curved lines. So linear functions, straight, non.
Now there we go. So I did what he asked yesterday, and our accuracy increases, but then it decreases again, hinting that it's still random. So
Linear
there might be
functions.
something
Now,
else,
this is one of the
which
beautiful
would be
things
hopefully
about
the final
machine
piece of the
learning.
puzzle.
And I'm not sure about you, but when I was in high school, I kind of learned a concept called line of best fit, or y equals mx plus c, or y equals mx plus b, and it looks something like this. And then if you wanted to go over these, you'd use quadratic functions and a whole bunch of other stuff. But one of the most fundamental things about machine learning is that we build neural networks, and deep down, neural networks are just a combination. It could be a large combination of linear functions and nonlinear functions. So that's why in torch.nn we have nonlinear activations, and we have all these other different types of
Oh, we
layers.
haven't set the
but-
playback speed to 2x. That's why I feel he's speak. That's why I felt he was speaking rather slow today.
Essentially what they're doing deep down is combining straight lines with, we go back up to our data, non-straight lines. So of course our model didn't work before because we've only given it the power to use linear lines. We've only given it the power to use straight lines, but our data is what? It's curved. Although it's simple, we need non-linearity to be able to model this data set. And now let's say we were building a pizza detection model. So let's look up some images of pizza, one of my favorite foods, images. Welcome back. In the last few videos, we've been harnessing the power of non-linearity, specifically non-straight line functions, and we replicated some here. And welcome back. In the last video, we saw that the model that we've been building.
Although we did cover a major part of this segment, I believe.
Straight too hard. And linear functions, we haven't seen any non-linear layers just yet. Or maybe we've hinted at some, but that's all right. Only pizza, but you, we'll get out of it all. What? And non-straight lines. But we've got non-linear. Before we write linear lines, so we've seen previously that we can build, I've got a function, if you wanted to learn more, classification model with non-linearity. And of course, if you wanted to, you could look up what is a non-linear function. If you wanted to learn more. Non-linear means the graph is not a straight line. Oh, beautiful. So that's how I learned about non-linear functions. But while we're here together, how about we write some code? So let's go build a model with non-linear activation functions. And just one more thing before, just to re-emphasize what we're doing here. Before we write this code, I just remembered, I've got a nice slide, which is the question we pose in other words linear. Layer 1 to a relatives how they are, model V2. Now, I'd like you to have a think about this, and my challenge to you is to go ahead and my challenge to you to the TensorFlow playground, something like this. So we've got two layers with 5. It's a little bit different to our 0.1, so we'll leave that. So this is the TensorFlow playground here and see what happens. It's not too difficult to do. We've got 2 hidden layers and 5 neurons. We've got our data set, which looks kind of like ours, but the main points here I have a learning rate of 0.1, which is what we've been using. But to change it from, we've previously used a linear activation. To change it from linear to ReLU, which is what we've got set up here in the code. It's what we've been too difficult to I'll finish in here. Well, what do we so build some code and see if this model works. But we're going to go through that over the next few videos. And also, my other challenge to you is to go to the TensorFlow playground and recreate our neural network here. You can have 2 hidden layers. Does this go to 10? Well, it only goes to 8. We'll keep this at 5. So build something like this. So we've got 2 layers with 5. It's a little bit different to ours because we've got 2 layers with 10. And then put the learning rate to 0.01. Well, what do we have? 0.1 with stochastic gradient descent. We've been using 0.1, so we'll leave that. So this is the TensorFlow playground. And then change the activation here. Instead of linear, which we've used before, change it to ReLU, which is what we're using. And press play here and see what happens. I'll see you in the next video. Welcome back. In the last video, I left off leaving the challenge of recreating this model here. It's not too difficult to do. We've got 2 hidden layers and 5 neurons. We've got our data set, which looks kind of like ours. But the main points here, I have a learning rate of 0.1, which is what we've been using. But to change it from, we've previously used a linear activation. To change it from linear to ReLU, which is what we've got set up here in the code. Now, remember, ReLU is a popular and effective nonlinear activation function. And we've been discussing that we need nonlinearity to model nonlinear data. And so that's the crux of what neural networks are. Artificial neural networks, not to get confused with the brain neural networks, but who knows? This might be how they work too. I don't know, I'm not a neurosurgeon or a neuroscientist. Artificial neural networks are a large combination of linear, so this is straight, and non-straight, nonlinear functions, which are potentially able to find patterns in data. And so for our data set, it's quite small. It's just a blue and a red circle, but this same principle applies for larger data sets and larger models, combined linear and non-linear functions. So we've got a few tabs going on here. Let's get rid of some. Let's come back to here. Did you try this out? Does it work? Do you think it'll work? I don't know. Let's find out together. Ready? 3, 2, 1. Look at that. Almost instantly, the training loss goes down to 0 and the test loss is basically 0 as well. Look at that. That's amazing. We can stop that there. And if we change the learning rate maybe a little lower, let's see what happens. It takes a little bit longer to get to where it wants to go to. See, that's the power of changing the learning rate. Let's make it really small. What happens here? So that was about 300 epochs. The loss started to go down. If we change it to be really small, oh, we're getting a little bit of a trend. Is it starting to go down? We're already surpassed the epochs that we had. So see how the learning rate is much smaller? That means our model is learning much slower. So this is just a beautiful visual way of demonstrating different values of the learning rate. We could sit here all day and that might not get to lower, but let's increase it by 10x. And that was at over 1,000 epochs and it's still at about 0.5, let's say. Oh, we got a bit. Oh, we're going faster already. So not even at 500 or so epochs, we're about 0.4. That's the power of the learning rate. We'll increase it by another 10x. We'll reset, start again. Oh, look at that, much faster this time. That is beautiful. Oh, there's nothing better than watching a loss curve go down. In the world of machine learning, that is. And then we reset that again, and let's change it right back to what we had, and we get to 0 in basically under 100 epochs. So that's the power of the learning rate, little visual representation. Speaking of learning rates, it's time for us to build an optimizer and a loss function. So let's write here. We've got our nonlinear model, set up, loss, and optimizer. You might have already done this because this is code that we've written before, but we're going to redo it for completeness and practice. So we want a loss function. We're working with logits here, and we're working with binary cross entropy. So what loss do we use? Binary cross entropy. Sorry, we're working with a binary classification problem. Blue dots or red dots. Torch.optim. What are some other binary classification problems that you can think of? We want model 3. parameters. They're the parameters that we want to optimize this model here. And we're going to set our LR to 0.1, just like we had in the TensorFlow playground. Beautiful. So some other binary classification problems I can think of would be email, spam or not spam, credit cards, so equals fraud or not fraud. What else? You might have insurance claims equals who's at fault or not at fault. If someone puts in a claim speaking about a car crash, whose fault was it? Was the person submitting the claim, were they at fault? Or was the person who was also mentioning the claim, were they not at fault? So there's many more, but they're just some I can think of off the top of my head. But now let's train our model with nonlinearity. Woohoo! Oh, we're on a roll here. Training a model with nonlinearity.
I've
so
already
introduce a nonlinear activation function within a model. Remember, this is a linear activation function.
created
and
the
if we train
function,
this, the
so
loss
I
doesn't go
think
down.
we need
But
to do
if we
that
adjust this,
again.
add a relu in here, we get the loss going down. So hopefully this replicates with our pure Pytorch code. So let's do it, hey? So we're going to create random seeds. Because we're working with CUDA, we'll introduce the CUDA random seed as well. Torch.manual seed. Again, don't worry too much if your numbers on your screen aren't exactly what mine are. That's due to the inherent randomness of machine learning. In fact, stochastic gradient descent, stochastic again stands for random. We're just setting up the seeds here so that they can be as close as possible, but the direction is more important. So if my loss goes down, your loss should also go down on target device. And then we're going to go xtrain. So this is setting up device agnostic code. We've done this before, but we're going to do it again for completeness, just to practice every step of the puzzle. That's what we want to do. We want to have experience. That's what this course is. It's a momentum builder. So that when you go to...
You know what, let's even though we did write the training loop, let's just do it again.
other repos and machine learning projects that use Pytorch, you can go, oh, does this code set device agnostic code? What problem are we working on? Is it binary or a multi-class classification? So let's go loop through data. Again, we've done this before, but we're going to set up the epochs. Let's do 1,000 epochs, why not? So we can go for epoch in range epochs. What do we do here? Well, we want to train. So this is training code. We set our model3.train. And I want you to start to think about how could we functionize this training code. We're going to start to move towards that in a future video. So one is forward pass. We've got the logits. Why the logits? Well, because the raw output of our model without any activation functions towards the final layer, classified as logits or called logits. And then we create ypred, as in prediction labels, by rounding the output of torch.sigmoid of the logits. So this is going to take us from logits to prediction probabilities to prediction labels. And then we can go to, which is calculate the loss. That's from my unofficial Pytorch song, calculate the loss. We go loss equals loss fn, y logits, because remember, we've got BCE with logits loss, and takes in logits as first input. And that's going to calculate the loss between our model's logits and the y training labels. And we will go here, we'll calculate accuracy using our accuracy function. And this one is a little bit backwards compared to Pytorch, but we pass in the y training labels first. But it's constructed this way because it's in the same style as scikit-learn. 3, we go optimize the zero grad. We zero the gradients of the optimizer so that it can start from fresh, calculating the ideal gradients every epoch. So it's going to reset every epoch, which is fine. Then we're going to perform backpropagation. Pytorch is going to take care of that for us by calling loss backwards. And then we will perform gradient descent. So step the optimizer to see how we should improve our model parameters. So optimizer.step. Oh, and I want to show you, speaking of model parameters, let's check out model3.static. So the relu activation function actually doesn't have any parameters. So you'll notice here, we've got weight, we've got bias of layer 1, layer 2, and layer 3. So the relu function here doesn't have any parameters to optimize. If we go nn.relu, parameters, let's check out model3.static. So the relu activation function actually doesn't have any parameters. So you'll notice here, we've got weight, we've got bias of layer 1, layer 2, and layer 3. So the relu function here doesn't have any parameters to optimize. If we go nn.relu, Does it say what it implements?
See, so we are layer 1, layer 2, layer 2 bias. Okay, layer 1 weight, layer 1 bias, layer 2 weight, layer 2 bias, layer 3 weight. There is no ReLU layer here, is there?
There we go. So it's just the maximum of 0 or x. So it takes the input and it takes the max of 0 or x. And so when it takes the max of 0 or x, if it's a negative number, 0 is going to be higher than a negative number. So that's why it zeros all of the negative inputs. And then it leaves the positive inputs how they are, because the max of a positive input versus 0 is the positive input. So this has no parameters to optimize. That's why it's so effective, because you think about it, every parameter in our model needs some little bit of computation to adjust. And so the more parameters we add to our model, the more compute that is required. So generally, the kind of trade-off in machine learning is that, yes, more parameters have more of an ability to learn, but you need more compute. So let's go model3.eval, and we're going to go with torch.inference mode. If I could spell inference, that'd be fantastic. We're going to do what? We're going to do the forward pass. So test logits equals model3 on the test data. And then we're going to calculate the test pred labels by calling torch.round on torch.sigmoid on the test logits. And then we can calculate the test loss. How do we do that? Equals loss fn on test logits versus y test. And then we can also calculate the test accuracy. I'm just going to give myself some more space here so I can code in the middle of the screen. Equals accuracy function on what? We're going to pass in y true equals y test. And then we will pass in y pred equals test pred. Beautiful. The final step here is to print out what's happening. Now, this will be very important because, one, it's fun to know what your model's doing, and two, if our model does actually learn, I'd like to see the loss values go down and the accuracy values go up. As I said, there's nothing much more beautiful in the world of machine learning than watching a loss function go down, or a loss value go down, and watching a loss curve go down. So let's print out the current epoch, and then we'll print out the loss, which will just be the training loss, and we'll take that to 4 decimal places, and then we'll go accuracy here, and this will be acc, and we'll take this to 2 decimal places, and we'll put a little percentage sign there, and then we'll break it up by putting in the test loss here, and we'll put in the test loss, because remember, our model learns patterns on the training data set, and then evaluates those patterns on the test data set. So, and we'll pass in test acc here. And no doubt there might be an error or two within all this code, but we're going to try and run this because we've seen this code before, but I think we're ready. We're training our first model here with non-linearities built into the model. You ready? 3, 2, 1, let's go. Oh, of course. Module torch CUDA has no attribute manuals are. Just a typo. Standard manual. There we go. Had to sound that out. Another one. What do we get wrong here? Oh, target size must be same as input size. Where did it mess up here? What do we get wrong? Test loss, test logits on y test. So these two aren't matching up. Model 3 x test and y test. What's the size of? So let's do some troubleshooting on the fly. Hey, not everything all.
Have to squeeze it. That's the reason. Okay. Anyhow, our ground truth should be y test, and our prediction should be test spread.
Model 3 x test.
Let's just copy the print statement from the previous training loop that we had. Now this doesn't have the accuracy percentage now. Just go back. Yeah, this should do it. This should be better.
So these two aren't matching up. Model 3 x test and y test. What's the size of? So let's do some troubleshooting on the fly. Hey, not everything always works out as you want. So length of x test. We've got a shape issue here. Remember how I said one of the most common issues in deep learning is a shape issue? So we've got the same shape here. Let's check test logits.shape and y test.shape. We'll print this out. So 200. Oh, here's what we have to do. But that's what we missed. Squeeze. Ah, see how I've been hinting at the fact that we needed to call squeeze? So this is where the discrepancy is. Our test logits.shape, we've got an extra dimension here. And what are we getting here? A value error on the target size, which is a shape mismatch. So we've got target size 200, must be the same input size as torch size 201. So did we squeeze this? Oh, that's why the
Bit 2, not here.
training worked. Okay, so we've missed this. Let's just get rid of this. So we're getting rid of the extra one dimension by using squeeze, which is the one dimension here. We should have everything lined up. There we go. Okay, oh, look at that. Yes. Our accuracy is
My accuracy isn't increasing.
gone up, albeit not by too much. It's still not perfect. Ideally, we'd like this to be towards 100%, the loss to be lower.
Maybe it's something to do with the way that and look at this, my loss is actually increasing here. Test loss. Yeah, the other loss is decreasing, but still.
but I feel like we've got a better performing model, don't you? Now that is the power of nonlinearity. All we did was we added in a ReLU layer, or just two of them.
Let's just see whether that has actually applied itself to self.relu. Then we did self.relu again. That is applied itself to 10, 10, 10, 10, 1. Okay, the in and out features match correctly. Maybe it's to do with our
ReLU here, but what did we do?
optimizer
We gave our
perhaps.
model the power of straight lines, straight linear, of
Show me
straight
you're
lines
learning
and
the
non-straight lines. So it can potentially draw a line to separate these circles. So in the next video, let's draw a line
show me your
and non-straight lines. So it can potentially draw a line to separate these circles. So in the next
okay, you know what, let's just bring it ourselves. So for the optimizer, I'm gonna put 0.001. Let's see what that comes out to be. And
video, let's draw a line, plot our model.
maybe it's with the way that we print our test flows perhaps. To text just explain why logits.
Decision boundary using our function and see if it really did learn anything. I'll see you there. Welcome back. In the last video, we trained our first model, and as you can tell, I've got the biggest smile on my face, but we trained our first model that harnesses both the power of straight lines and non-straight lines, or linear functions and non-linear functions.
What are we doing wrong here?
And by the 1000th epoch, we look like we're getting a bit better results than just pure guessing, which is 50% because we have 500 samples of red dots and 500 samples of
We are not using a GPU,
dots, so we have
but
evenly
I
balanced
mean,
clusters. Now, we've seen that if we added a ReLU activation function
that
with a dataset similar to ours,
can't
flow
be
playground,
it,
the
can
model
it?
starts to fit, but it doesn't work with just linear. There's a few other activation functions that you could play around with here. You could play around with the learning rate, regularization. If you're not sure what that is, I'll leave that as extra curriculum to look up. But we're going to retire the TensorFlow playground for now because we're going to go back to writing code. So let's get out of that. And let's get out of that. We now have to evaluate our model because right now it's just numbers on a page. So let's write down here 6.4 automation function patterns in vector mode. Dots in troubles in threads. We want them to be in the same format as our.
Now our accuracy hasn't increased, but we have to fix this before we move on. So let's see what we can do here. Maybe I mean, it doesn't say model v3. Does it say model v3 for him though?
Test and launch two of our functions at equalization if you're not evenly balanced class. Getting a model that harnesses. Welcome back. In the last video, we trained our first functions, and by the 1000th epoch, we trained our first logits.shape. We've got .squeeze, and not everything always works out as you want. So
You put the learning rate as 0.1. I mean, that can make much of a difference, can it? Let's put it as 0.1 itself. Oh, maybe it can because, but let's just see. Model v3. Okay, loss function, and here we go. Nah, that didn't do anything. It's still obvious that it's just guessing. Maybe something to do with the way that we predict accuracy, perhaps. I mean, the test and the test loss too. Something's up there. Something's up there. So with model 3 excess squeeze, we activate it using the sigma out function. What can be the issue here? Test logits by test. Okay. We are using BC with loss itself, right? Because then and only then can we pass logits. Otherwise, we need to activate it. Yeah. That can be it then. Maybe, let's just open up we learn pytorch.io and just .io website. Let's there should be the notebook here, right? Let's just see what yeah, go to site. Let's just do model 3. Yep. Okay. So mm-hmm. Let's compare the model first. Can also put sigmoid in the model. This would mean you don't need to use it on the prediction. This would can also put sigmoid in the model, or meaning we don't need to use torch dot. Oh, you mean we can use it here itself if we put sulfur sigma. Okay. Anyhow, that's besides the point. Let's see what happened here. It's exactly the same. We have our loss function. Where's our? Let's go back to model 3. We pass it the model 3 dot parameters. I'm just gonna copy this to make sure I'm on the yeah, let me just copy this code. See, actually, you know what, let's put it in a new. How to enter just a new block? Yeah, is there a shortcut? Or control plus M B? Okay, or control plus M or B, maybe that's what it meant. Nope, I just want this part of it. Okay, let's see. Huh, that that worked. So wait, what's happening? What's the difference between this and this? The toaster panel seat, epoch, in the order that it comes, it is different, but that shouldn't. Maybe I'm assigning the wrong X and Y train perhaps. That's all good too. So we calculate the logits first, and hmm, I mean he's still go using model dot train, but I mean that can be it, kind of. Okay, we'll test it out. Accuracy y true is y train and y bread. All good, all good. Then what? It show me the loss again. Of course, of course. Ah, I get it now. I put in Y predictions. Like we can't come back. This will come back here again. This my code. That is my code. I get it. So, then why do we need? Oh, wait. Anyhow, the thing is that we can't compare Y logits to Y predictions. We need to compare to Y the training set, right? Here we're just comparing like the same thing to the same thing. Maybe there's a slight difference. So that would be it. And what about in Teslas you're doing it? Test flows you're doing it, right? There we go. Okay. You know what? Just for the sake of it, I'm gonna delete this cell and I'm gonna model 3 again. Instantiate that, instantiate this, and run that. Bring it to the same level. There we go.
So length of x
That's
test, we've got a shape issue here. Remember how I said one of the most common issues in deep learning is a shape issue? So how and one using like yeah, but what
so
do
now let's
we
move
train
on
model?
to the
We'll put it
next.
into eval mode, and then we'll set up inference mode. Could functionize this, of course. Beautiful. And then we'll go ypreds equals torch dot round. And then torch dot sigmoid. We could functionize this, of course. Model 3 and then pass in x test. And you know what? We're going to squeeze these here because we ran into some troubles in the previous video. I actually really like that we did because then we got to troubleshoot a shape error on the fly because that's one of the most common issues you're going to come across in deep learning. So ypreds, let's check them out, and then let's check out y test. We want y test 10. So remember, when we're evaluating predictions, we want them to be in the same format as our original labels. We want to compare apples to apples.
Pass
We compare
in
the
the
format here.
logic
So these two things are the
cell, and
same
we are
because they do,
gonna
they're both on CUDA,
squeeze this.
and they're both floats. We can see that it's got this one wrong, whereas the other ones look pretty good. This one look pretty good. In predictions, we want them to be in the same format as our original labels. We want to compare apples to apples. And if we compare the
Compare the predictions with what they should be. Not the first 10. Tracker was never closed.